I'd like to welcome everyone here for our first Optimus Prime in-world challenge. The presentation will be from Team 5. Team Leader Melissa and Rachel, you may take it from here, and please remember it's your responsibility to get us from this portal to your world and then back again. It is 3:06. You will have a full 30 minutes time. Please don't worry about the fact that we're starting a little bit late. And as we keep moving through your space, the evaluators here may have some questions. I'll text chat if they have a question so that I don't interrupt you, and we'll try to take those when it's most convenient for you. Thank you all.
Okay, so hi everyone. It is so great to have you here today. My name is Rachel and this is Team 5. So we have a great presentation for you today. So thank you all so much for your time and the opportunity to share our JWST spinoff with you. So right now we are in the real world in-world entrance room that I helped to design this past summer while interning at NASA Goddard Space Flight Center. So if you would follow me up these stairs, we can start going to the world. So going up these stairs, we will take a right, and then here on the walls we have information about JWST. And then if you just follow the path and then take another right, we can continue along this walkway. So when you're at the end of the walkway, then you take a left, and then you will see a sign that says, click to teleport to the team spaces. So when you see that sign, we will click on Team 5 so we can teleport to the world.
My name is Zach, and our team consists of me, my sister Rachel, and our college mentor Melissa. We will introduce ourselves more thoroughly in 1 minute.
Yeah, so this is the entrance of our world. On these walls here, we have the steps to the design process, which we briefly explain to introduce you to our world before we walk through in detail. So turning to the left, the problem that we defined at the beginning of the process was how to design a JWST spinoff using current technology to make this applicable in new circumstances on the commercial market. So right now we'll just briefly go through some of the signs on the walls here.
Afterwards, we conducted background research. We chose interferometry to spin off because we thought their measurements of small displacements were interesting. We thought this was a good idea, but did not know in what circumstances the precise measurements of interferometers could be used. We then brainstormed solutions to the design problem, and then chose the best solution, as we will discuss later. Feel free to take a minute to check out our design process overview before we move into the details of our world.
So we will start by turning to our right, which will bring us into our world. Here we have a NASA sign, and walking along this pathway into our world, we can see that on the left-hand side, we see our team logo that we designed. Our team name is Celestial Galaxy because the James Webb Space Telescope is designed to see millions of light years away. With the creation of this telescope, we will be able to see back in time to the formation of the universe. We thought that our team name was applicable to the JWST mission.
Also, we see that if we click on these signs, we can teleport to learn more about our team members. Let me just say, learning how to create teleports was a difficult process, but we worked through the problems and finally got the teleports to work correctly. So here, we will all click on the sign that says click to learn more about Zach. My name is Zach, and I am a high school freshman interested in computer science. I also love to swim competitively. My favorite subject in school is math. I also really like cats, as seen by this picture on the right. Now we will click the teleport back sign.
Now, going along the path, we will all click on the learn. So now we will all click on the learn more about Rachel sign. Okay, awesome. So my name is Rachel, and I'm a high school junior interested in STEM. I also swim competitively like Zach. In my free time, I like to produce videos and post them to YouTube and also volunteer. This picture here on the left-hand side is from the 2014 NASA luncheon, where I gave a speech to over 300 interns, mentors, and NASA employees. Now we will click teleport back sign.
Okay, now we can click on the Melissa College Mentor sign to learn a little bit about me.
Okay, so firstly, I'd like to thank you all for coming to our presentation today. My name is Melissa, and I'm the college mentor for Team 5. I'm currently wrapping up my master's degree at the University of Buffalo, where I'm studying industrial and systems engineering. And I'll be heading to the University of Michigan in the fall to earn my PhD. Last summer, I worked as an intern at NASA Langley with the Complex Aerospace Systems team. And I will be doing my dissertation on work that I began there at Langley. I heard about the Optimus Prime Challenge through Langley, and I'm so happy to have had the opportunity to work with Rachel and Zach. They're a great team, and we're really excited to show you what we've prepared today. So let's teleport back by clicking the teleport back sign and get started.
So if we turn 180 degrees and look up, we can see a model of the Hubble Space Telescope. Hubble is the predecessor of the James Webb Space Telescope. Launched in 1990, Hubble is still operating today. JWST will be a more powerful telescope than Hubble, which is why JWST is being created, in order to gain more information.
So, walking inside this building here, we will be able to see our JWST model. The James Webb Space Telescope is going to replace the Hubble telescope. Planned to be launched in 2018, JWST is a large infrared telescope that will study the history of our universe. JWST is by far my favorite telescope of all time because it is so innovative. It has a large mirror that is folded up during launch, but will then unfold afterwards.
The innovative JWST technology is very interesting. Their unique ways to solve problems directly impacts the spin-off we chose. Turning to the left, we're going to walk down a hallway.
Hey guys,
Where are you stuck?
We're trying to figure out how to get out of your little introductory box.
If you click the sign, the sign on the wall that says teleport back will teleport you back into the real world.
Rachel, I think we've got him. I just invited him. You can keep going.
Okay, thank you. So we are in this hallway right now, and so the JWST technology we chose is the aspheric stitching interferometers. Interferometers are used in the optics industry to measure lens surfaces that are not a normal shape. They measure multiple zones on the lens surface, then stitch the data together mathematically to determine any irregularities. At the end of the hall here, we can see two images of an interferometer taking measurements to stitch into a single image of the surface, making the measurements very accurate.
Walking down this long hall, we see that the James Webb Space Telescope uses interferometer technology, but the engineers modified the interferometry to fit their needs. Normally, a phase-shifting interferometer will be used to measure the optics to verify their precise shape. NASA tests all JWST's parts in conditions similar to that of space in order to ensure their functionality. But the JWST mirrors are large, 21 feet and 4 inches, so the traditional phase-shifting interferometer would not work. So they created dynamic interferometry that could take measurements more quickly as compared to the old interferometers. This technology is used today in fields such as optics, astronomy, manufacturing, and medical industries.
So we want to take the JWST interferometer technology and use it in other fields such as aerodynamics and hydrodynamics to make submarine propellers and helicopter blades more efficient. So now at the end of this long hallway, we are going to enter a room and then we're going to turn to the left. On the left-hand side, we see that some of the ideas that we brainstormed in the beginning did not work. We thought that we could use interferometry to make ceiling fans quieter and sculptures more accurate. However, this would not be very feasible because even though ceiling fans would be quieter and able to move more air, the fan would become 10 times more expensive. Also, replicating famous statues would also be very costly, and sculptures do not need to be created with such high accuracy that the interferometers would provide us.
On this back wall, we have some sketches of our design. When engineers are designing a product, they always have target specs in mind. That is, they use mathematics to determine the best conditions for optimal performance of the product. These target specs can come in the form of angle measures, material stiffness and thickness, and surface texture, among many others. However, the finished product isn't always perfect and doesn't always meet the precisely calculated target speculations. Although the product may seem to perform well enough, current measurement tools can give us a pretty good idea of what the surface of a helicopter blade or submarine propeller may look like. But applying interferometry to this and could generate some truly revolutionary results. If we can examine the surface of a helicopter blade or submarine propeller using the precision of interferometry, engineers will be able to detect minute imperfections that can be refined in the next iteration of the product, resulting in even quieter, more efficient, and aero/hydrodynamic propellers than ever before.
So here in the middle of the room, we have a model of the interferometry design. The laser is shooting into a prism which splits the laser beam and hits the object being measured. This measurement is then captured by the imaging and sent to the computers located here. The computers take thousands of measurements and then stitch them all together into one coherent picture. The coherent picture generated allows engineers to reshape the propeller to perfection using the computer controller Miller machine.
So, turning around to look at this back wall, we can see a computer that is making the readings and will stitch the information together. The tools we use to create the 3D in-world models are Cinema 4D and Accutrans 3D. We use Cinema 4D to create the models and Accutrans to convert and scale the models into the RWX 3D format.
So, walking down this hallway, we have an overview of our helicopter.
Rachel, we do have a question for you. Mark Clampton was asking why you are shooting through a prism.
We have to shoot through a prism so that it diffracts the laser beams so then it can create the really accurate measurements, because if it was just straight on, the laser wouldn't be diffracted. So then with the diffractions, it can send the more precise measurements to the computer milling machine that we showed. So that allows for the more accurate measurements of the blades and other objects that we want to use the interferometry design for. Awesome. So, walking down this hallway, we have an overview into our helicopter blade room. So, turning to the left halfway down the hallway, we can enter this room. So we thought that interferometry could be used for helicopter blades because military operations require stealth for their helicopters. Helicopter noise is a problem today, and using interferometry would be a way to make the blades operate more quietly.
In this room, we have basic information about helicopters, like how helicopters create aerodynamic lift force that can support the weight of the helicopter and make it fly. Helicopter blades create loud noise because the blades are chopping through eddies in their own wakes, known as blade vortex interaction. Helicopter blades need to have blade geometry, stiffness, and structural response. Otherwise, these can have effects on the performance and acoustics of the helicopter. Blade accuracy leads to low noise and low vibration helicopters.
We are going to use interferometry to obtain blade shape measurements, which will allow us to reshape the blades with extreme accuracy. These improved blades will allow us to make quieter, more fuel-efficient helicopters. This is very important because military helicopters can avoid detection by making less noise, civilian helicopters can operate at night in populated areas, and the helicopter would be more fuel-efficient, thus saving natural resources.
Alright, now we will exit this room by going back out the way we came, and then continue down the hallway to the submarine room. Submarine propellers are different from land vessel propellers in that submarine propellers must have a low acoustic signature. Since a hydrodynamic flow dominates the performance of the sonar system, we are going to use our interferometer laser and speckle pattern interferometer technology to measure the propeller to see how we can make the design quieter and more efficient.
Bubbles caused by the propellers are noisy, so all propellers are designed and shaped to reduce bubbles while still maintaining speed and efficiency. The measurements taken by the interferometer have a 10 to the negative 7th degree error. If this error in the calculations of the blade can be refined to get rid of the 10 to the negative 7th error, then the resulting blades will have a more hydrodynamic design.
Using interferometry to accurately measure submarine propellers will allow for quick and quiet movement underwater that is critical for a submarine stealth. When the propellers are not accurate, this costs fuel and speed, so our design will fix this problem.
So if you look on this picture on the back wall that has the flags on it, here we see that a graph that compares the quietness of blades of the United States, Soviet Union, and Italy. As one can see, the USA has flatlined for the past 15 years in noise levels. With the technology, the United States can further reduce the noise levels to improve the interferometer design. Using interferometry can help the United States compete with the other nations.
In the corner of this room, we have the computer-controlled milling machine that will allow engineers to reshape their propeller to perfection using the measurements from the interferometry. And in the middle of the room, we have the laser system measuring the submarine propeller.
So walking down this final hallway, we want to reflect on the 2 reflection questions. As a team, we overcame any difficulties throughout the process with communication. We discussed the design process steps as a team to come to a concise, coherent decision. Everyone was able to contribute ideas and no ideas were shot down. We allowed for the flow of ideas, listening to everyone's opinions and considering what he or she had to say. We had team communication difficulties at the beginning stages of the competition due to busy and conflicting schedules. However, we were able to overcome this by effectively communicating and replying to.
As a result of this challenge, the team developed effective communication skills. Communication is key to creating a project we are proud of. Communication is also paramount in real life and in the workplace. Also, the team members learned how to use 3D CAD software. Never using a program like this before, we taught ourselves how to maneuver around, build objects, and create a world to showcase our spin-off. We also learned how to research using higher-level sources like Google Scholar and online databases.
So on this back wall here at the end of the hallway is our business case. So our business case is that large contracting companies such as Boeing, Lockheed Martin, and Northrop Grumman, which are large defense contractors who would benefit from the use of the interferometry design. They sell planes to the military and would pay for better maps of wings because stealth of planes is crucial in military operations, so one would pay more money in order for the planes to be quieter. The success of high-security missions depends on the precise measurements from the interferometers. For example, Boeing sells many defense aircraft such as the AH-6 light attack helicopter and AH-64 Apache, and has customers in 150 countries such as Germany, Italy, and China. The Boeing Defense Unit is the largest business unit, containing 2,100 employees. Lockheed Martin also sells aircraft and naval systems with its collaborators. Lockheed Martin has a proud legacy of providing innovative naval systems for the United States and its allies. They can continue this path of innovation by adopting our interferometry design to make the defense vehicles more powerful to compete with the other countries.
And that will conclude our presentation. And we've been stressing these points throughout the entire thing, and we wanted to say that we are so grateful to have the opportunities to compete, and we have learned so much about NASA, STEM, patents, and the modeling process throughout. We really appreciate your feedback, help, and support throughout the process.
So thank you all so much, and if you have any questions, we would love to answer them. But if not, at the end of the walkway here, there is a teleport back to the real world, in-world location. So we thank you all so much, and we had a great time doing this.
Thank you to our evaluators, and I just want to thank Team 5. Rachel and Zach, you really did an excellent job. I had so much fun working with you. And to the judges, I hope you all enjoyed our presentation because we had a blast putting it together. So thanks again.
You guys can hold tight for a moment. Let me check and see if there are questions from the evaluators here at Goddard. The evaluators on this end are very impressed. Thank you for all of your hard work. Becky, are there any questions from the evaluators on your end?
Yeah, this is Eric. We are having technical difficulties, so we're just going to walk around for a couple minutes to get caught up.
Rachel, Zach. We have a question from our evaluators here. We'd like you to discuss more if you really think an interferometer is needed for manufacturing of the helicopter blades and the items that you were considering. And can you persuade us to believe that there is need for an interferometer for those kinds of manufacturing needs?
Yes, so we definitely believe that the interferometry design would be paramount to helicopters and submarines. They would be really important because of stealth. For example, like with the military helicopters, if they are making sounds, then that would allow for detection from the other countries. So if we were to go to war and be in a dispute with another country, we would not want our secret military submarines or helicopters or even airplanes to be detected, because that would give away our position and therefore mess up our security in the operation. And also that interferometry design would be helpful to help make them also more fuel efficient. Right now, the fuel efficiency is high because they are wasting gas on the not well cut blades. So with the interferometry and to create the more aerodynamic blades, this would help the fuel economy and then cost less gas and less money. So it would help make our economy and also the environment more safe and then less pollution. So that's always a plus. The posters about the interferometer, there is one in the submarines section that talks about the difference in the United States versus USSR and Italy. On the back wall, it has a graph picture that talks about the noise levels. And then also there are posters in the first room that we visited that has our sketch design and then images of the interferometry.
Becky, Eric, Chris, do you have any questions from your end?
So we're just kind of walking through and getting all caught up still. So we're just about to go into the spin-off section.
Great. No worries with that. If you want, we can also come back toward the end and have a chance to tour around so you can see the other pieces that are there. Team 5, will you please get us back to the real world portal? Thank you so much for all of your time. It is evident that you put a lot of hard work into this world, and we're all very impressed here at both NASA Goddard and at the National Institute of Aerospace. Please take us back.
Thank you all so much. We had an awesome time learning about this, and we've learned so much throughout the process. So in order to get back to the real world in-world portal area, at the end of the presentation, at the last hallway, before you go back to the JWST area, there is a purple light, and then it says teleport back to real world in-world. So if you walk right into that portal, then you can teleport back. So thank you all so much for your time.